very much, and thanks for having me here. It's a great privilege. I was going to start with a little bit of history of radio astronomy, and then move on to a little bit of the radio astronomy that you can do with a small dish, tiny dish, and then a little bit about Goonhilly, if that's okay with you. There'll be a break between each one, I think, while Sean fights the computer. I expect to find the next presentation. But here goes. This dish was given to me very kindly by a guy who'd done a lot of work in the development of satellite TV in the early analogue days, and he had it in a little paddock in the Peak District National Park. And when he moved, it was a condition of planning that he had to move all the dishes, so he gave them away. I was lucky enough to get this one, and I've haven't looked back since. Okay, thank you very much. Right, first of all, why radio astronomy? This is a very old image which has been around for years, and is a black and white image of M81 in optical, black and white, and in radio, looking at the radiation from neutral hydrogen. And I think you can see straight away that by looking at the radiation in neutral hydrogen, you see more. You can see that these objects are indeed connected rather than being completely different objects. So that's why we use radio, along with other wavelengths for astronomy. But radio is easy for us to use as we are all familiar with it. And because the atmosphere is more or less transparent at the part of the radio spectrum that we're going to be using. This chart talks about the opacity of the atmosphere at different wavelengths, and starting with the very short, very nasty wavelengths, gamma rays and X-rays. Luckily it's pretty well opaque. And then we get down to the visible part of the spectrum, where on a good day you can see through the atmosphere reasonably clearly. Then we move into infrared, where there are lots of absorption lines, but basically the transparency is a little bit better. Then it becomes in the high microwave part of the band, the atmosphere starts to get in the way again. But from here, about somewhere around about 3 sems until you get down to about 10 meters, the atmosphere is pretty well perfectly transparent. So you can do your astronomy at ground level without any problems. The other wavelengths, you've got to put your telescope into space, which is a little bit outside our remit. So where did it all start? It started with this guy, Jansky, who worked for Bell Telephone Labs in the 1930s, and he was looking at shortwave long-distance telephone circuits and finding there was interference and wondering where it was coming from. He was set out to investigate it, and he was a good scientist because he found that this interference, whilst it was changing on a daily basis, he was careful enough to note that it wasn't exactly on a daily basis. It wasn't changing at the rate at which the Earth rotates in relation to the Sun. It was in the relationship to the rate at which it rotates relative to the universe as a whole, the sidereal rate. And it's about 4 minutes a day or something different. So he knew that this interference was coming from outside our solar system. He wasn't an astronomer, so he was not particularly bothered about this, but he noted it. And then along came the great Reber, who I'm sure you must be all very familiar with, because I believe he ended his time right here. And he was a radio ham who built the first dish and made the first maps. His dish is in the Smithsonian Institute, I believe. And these are some of the maps that he made, which, guess what, they correspond to the Milky Way, various hotspots in the Milky Way. So that's really where it all started. This was happening during the 1940s, and of course there were enormous developments in radar at that time, and those involved with it noticed that there were effects occurring that weren't always an enemy bomber coming towards them to drop bombs on them. They might have had some other explanation, and after the war a lot of the radar equipment was purloined, gathered together, particularly by Bernard Lovell at Jodrell Bank, and they cobbled together the first bits of radio astronomy equipment at that location. Fundamentally, of course, all electromagnetic radiation is the same, whether we're talking about gamma rays or anything down to your low frequency stuff. It's of course when electrons or charged particles are accelerated, something we do with our radio gear by accelerating them backwards and forwards along the antenna, but it occurs in natural circumstances as well. There are a number of different types of radiation. I'm going to be mainly talking about spectral line types because of hydrogen we're going to be talking about. But we'll start with thermal. Thermal is the basically all the atoms are in motion. Everything above absolute zero is in motion all the time and is emitting radiation, as we know, as we move up into the higher frequency part of the spectrum. And we point our dish at the trees and the ground, we see the noise would need to go up, which can be irritating. So thermal is one type. Synchrotron is where electrons or charged particles are moving at speed in a magnetic field, and that causes them to spiral, and that causes acceleration and emission of radiation. Free is where there are charged particles moving at speed and interacting with one another without combining, and again they will be deflected as they pass each other, if you like, and that deflection is a form of acceleration and photons of energy are emitted. Finally, spectral lines, which we'll talk about a little bit more in a moment. A very good local source of thermal radiation, of course, is the sun. Wasn't too much of it today, but it emits a very broad spectrum of radiation. But all stars, or any body that emits radiation, the wavelength at which that radiation peaks is a subject to the temperature of the body, and Wien's law describes where that peak will be. In the case of our sun, it's around about 5,000 Kelvin, so it peaks in the yellow part of the spectrum. It doesn't mean that it's a narrow signal, it's a very broad signal, that's where the peak is. And if you were to go to, for those astronomers amongst you, look at a hot, it's a red star which is less hot, like Betelgeuse as I like to call it. It's a lower temperature, therefore it's in the red part of the spectrum. If you look at a hot star like Sirius, it's in the blue part of the spectrum, and that's why you see stars with different colours. If you break their light down into through a thing like a prism, then you start to see something interesting going on. You see that lots of bits of it are missing, and they are missing because atoms of different materials in the atmosphere of the star, in this case the sun, are absorbing the radiation, and that is a part of this spectral line process, which we'll go on to in a little bit more detail. But by analysing that allows astronomers to determine what elements are present in the atmosphere of the sun, or indeed of any star that they can gather enough light from to use this process. They can also see, as those lines are on a very precise part of the spectrum, you can also use them to very accurately measure the speed that other stars are moving relative to us, because they'll all be shifted by Doppler shift. We'll talk some more about that in a moment. The spectral line processes occur when energy falls on an atom and sends an electron into a higher orbit, and then when it drops back to its lower, more stable orbit, a photon of energy is emitted, and the energy in the photon depends on which shell it's dropping from, and when it drops back, and the action from different shells gives rise to emission of photons with different wavelengths, and those correspond to the wavelengths that where energy was absorbed. Where does the energy come from? Well, it comes from the local object. The star is spitting out energy all the time. Atoms will then absorb that energy by raising electrons into a different layer, and then they will naturally drop back. And to explain those missing dark lines, if you think that electron that was coming towards you has got absorbed by the atom, you say, well, it's going to emit it again, that's fine, why don't I see it? Well, you don't see it because it might go anywhere and not necessarily towards you. That's the explanation I like to use anyway. That really is enough of that for the moment. I'll come back to that in the next section when we start talking about hydrogen line. But now the moment of truth, will the sound work? What do you think?
The play to the left?
Is that... oh, right. Okay. That's clever, isn't it? Now that's the sound of the crab pulsar. If you have a really big dish, you can actually hear that, but with smaller dishes it's much more complicated. That's actually synchrotron radiation, because pulsars are neutron stars which have very strong magnetic fields and tend to be spewing charged particles out on a polar basis, so they're going north and south, if you like. They're spinning very fast. And if the beam is, if the magnetic field is slightly off-center and happens to be pointing roughly towards us, then we get this pulsing effect. A pulsar is a collapsed star, typically about 20 kilometers in diameter and with a mass of, say, 10 times the mass of the Sun, but contained in an object 20 kilometers in diameter. Incredible density, you know, a teaspoonful of it would weigh millions of tons. Quite interesting. It's really only in there just as a bit of fun. This is one of the antennas at Goonhilly, which we'll talk about a little bit more, but just to show how astronomy creeps in even when you're trying to get an old satellite dish up and running again and understand how well it's performing. One of the things we did down there was we pointed it at the Sun. This is, we've taken the IF of the equipment that we got connected to the dish into spectra view, probably through a FunCube dongle or something like that. This is the Sun, when we make it track the Sun. And you can see what we've done. We've gone from -27 to about plus to -7, so about 20 dBs of sun noise. Not particularly good, because we haven't got all the right gear in place, but it'll do. Then the next thing you want to do is to calibrate it using a known calibration point. There are various radio stars, as everybody calls them, radio stars. They're not really stars, they're supernova remnants that are emitting radiation. And astronomers use these and check the flux density, the signal strength, if you will, from these various sources. And it was very important that we checked to see that we were getting the right kind of level, and it also proves the pointing accuracy of the dish, because the Sun is not, when you get a big dish, the Sun is not a point source. It's half a degree wide, and if your beam width is 0.1 of a degree, it's not much help. This was great fun because at this stage we had got software which would track that big dish to the Sun and to the Moon, but not to celestial coordinates. The dish originally, of course, was designed for working with geostationary satellites, so it had a pointing system. You pointed at the satellite, and every now and then you could adjust it a little bit up, down, left, right, but it was not designed to track. And I'll show you a little bit about how we overcame that problem. And at this particular time, I didn't know how far the guys had got with the tracking software, and literally driving to the dish from the B&B we were staying in, it was revealed to me that they couldn't track, so I said, okay, we'll go back to a bit of very old-fashioned astronomy, where they used transits. So you had a telescope that would only go in elevation, and you watched the sky rotate past as the Earth rotates. So we worked out the azimuth and elevation for about 30 minutes ahead, which gave us time to trundle 400 tons of dish to the right direction. and we kept our fingers crossed and hoped that we would see a peak as it swept past, in this case, Taurus, I think it was, and that was the peak we recorded, so it was a mighty breathing of relief. Anyway, that's enough on the sort of history and introduction. Shall we try moving on to the next presentation? Any questions on that? Anybody like to ask any questions? I'll do my best to come up with a plausible answer.
So you said when you pointed at the sun there was like 20 dB more noise.
Yeah.
I would have thought it would be a lot more than that.
Yes, it should have been.
Okay.
That was, I think, that was on 3.4 gigahertz, and at that stage it was very early. Oh, you're looking for
Emission Line Astro 1?
yeah, that will do nicely. I'll show you later about the beam waveguide system, but I started off by explaining to the guys we're looking for this piece of rectangular pipe coming out of the bottom of this system somewhere, the waveguide. What size is it? I mean, it was that basic, and it turns out that all kinds of filters and things in the way, and when we actually tried transmitting into it, the return loss was 8 dBs. That was on 3.4 gigs, on 5, because the dish was designed originally for geostationary satellites up on 6 gigs, down on 4 gigs, and the filters cut off somewhere about 3.8, 3.9. By the time we get down to 3.4, we were struggling. So yeah, it wasn't particularly good, but it showed us. It did show the tracking was right. Okay, so I'm going to skip through some of these because you've seen them before. This is why we look at hydrogen. We spoke about the spectral line processes, and just to reiterate, when the electron drops back from one orbit to another, a photon of energy is emitted, and what we're going to be talking about is hydrogen. Hydrogen is the most abundant element in the universe, and very obligingly it transmits on 1420.405 something or other megahertz. Very precisely, it's one of the most precisely known numbers in science. And the mechanism that causes this is the flip of the spin of the electron around the nucleus, the proton of a hydrogen atom. A hydrogen atom has one proton, one neutron, and they're both spinning. And when it flips to the lower energy state, it emits this photon of energy, which is on 1420 megahertz. It gets excited to that state by incident energy from things like nearby stars, and flips back in its own good time. This is reckoned to occur about once every few billion years for a given atom. But there's so many of them out there that it's quite easy to find the signal, luckily. This is not the only spectral line that is of interest to radio astronomers, but it's really the only one that somebody with a small dish and building stuff out of the junk box can expect to do, is to receive hydrogen. These are some of the other spectral lines that occur in the microwave spectrum, and there you can see that they're useful to astronomers to determine what is present in certain sources of radio, the chemicals that are present, and that's why how so much has been learnt about various nebula and things that they can point at and detect these radiations. Now a bit of radio. So we have a dish, we have a feed. We're trying all the time to keep the T-sys down as low as we can, and luckily with the advent of high electron mobility transistors developed for the satellite TV industry, we can achieve quite incredible results. The system, my system, the T-sys is about 48 Kelvin. No refrigeration required to do that. So it's pretty sensitive. One of the things you're trying to do in designing the designing the feed is to make sure that you do not over-illuminate the dish and see ground noise from behind it. And in fact, the system I use is a dual mode feed, and it under-illuminates the dish. So we make sure we're not picking up stuff from behind. In my case, I convert the 1420 megahertz down to approximately 2 meters. Why? Because I had a 2 meter IF strip floating about which could easily be pressed into service. Why wouldn't you use it? We're going to be scanning across a range of frequencies. I'll explain why in a minute. And because you don't want any strange cable-induced effects, we always use precisely the same IF. So we're sweeping the local oscillator and keeping the IF constant. And that's all done under the control of a PIC. A programmable attenuator is there to make sure we get the levels right. The kind of dynamic range we're interested in is very, very small. 10 dBs of dynamic range would be plenty for anything you can do with a 3.7 meter dish. So the system consists of a clock that timestamps all the measurements. In my case, I use an SI570 programmable crystal oscillator to generate the local oscillator signal at sort of base band. If you like, it's then multiplied up. Very simple IF with a homemade, it was actually an FM IF strip with the FM detector thrown away and an AM detector replacing it, and a bit of few op amps and things to get to the level suitable for going into the A to D on a PIC. And this links to a PC over here, which will show you a bit more about what goes on in a moment. So there's the feed. It's basically dual mode. It's a fairly standard dual mode feed, but it's not circularly polarized. There's no need for that. It's linearly polarized. The down converter's out on the dish, and it's under illuminating the dish. Talk a little bit about the tracking system of the dish. If you're going to make observations, you've got to be able to know where you're pointing the dish and have it track as the Earth rotates, and as the Earth orbits the Sun. So you've got to, that's all taken into account on the tracking software. And I made another PIC-based system that talks to the computer tracking software. The complex maths, if you like, is done there. Simple RS-232 connection, microcontroller, and then an elevation and azimuth motors driven with pulse width modulation generated by the PIC. The PICs also read encoders. The azimuth encoder was a 4096 incremental encoder. There are some very good ones, about 4,000 pulses, that appeared on eBay very reasonably recently, and I think I wrote a little thing, and they're quite adequate for even a 3.7 meter dish, because you can double up, effectively turn it into I suppose an 8,000 pulse, or it might have been the other way around. Maybe it was a 2,000 pulse you can convert to 4,000 pulse, but very, very nice little units. I think they were Omron. They were appearing for quite reasonable prices. In my system, the elevation encoder was simply a reed switch and a magnet on the shaft of one of the drives, and it was perfectly adequate. That was producing about 20-something pulses per degree of elevation, and the azimuth encoder, as you see, 4,096 pulses for 360 degrees. So that's the tracking system. Tracking software was, I originally plagiarized from a book by the RSGB, Amateur Radio Software, 1981. I plagiarized that and wrote it in something like GW Basic. I'm not a wonderfully skilled producer of nice GUIs. And a friend of mine who came along and told me it was rubbish, which it was, and he got the job of producing this. So this is the software I use. There's all sorts of other software around, but it was fun using this. And we have tracking modes. We can make it track the moon or the sun or celestial coordinates, and it tells you, reads the computer clock, so it knows what the time of day is and where to point, and it talks to the gear that's controlling the dish simply in terms of azimuth count and elevation count as targets, and lets the pick sort that out at the dish. So what we're going to do is we're going to be scanning scanning a chunk of the band where we're expecting to find this hydrogen line radiation, and basically digitally watching the S-meter, if you like. Now, astronomers talk about brightness. They're obsessed by the brightness of objects, and the unit that they use to talk about brightness for radio astronomy is called antenna temperature. As I mentioned to you, the system temperature is, my system is about 48 Kelvin, and when you point it at the cold sky, you don't see any more than 48 Kelvin, but when something that's brighter on the frequency you're looking at hoves into view, the temperature goes up. So that's why we use antenna temperature as a unit. As I mentioned, we're going to scan the band around the frequency we expect to find the radiation. Why? When we know it's on precisely 1420.405, it's because it's all moving. And so it's all Doppler shifted. And this turns out to be very useful because we can start to see how the galaxy is moving, bits of the galaxy are moving, and we'll go on to more detail. So it's red shifted, i.e. the wavelength gets longer if it's coming towards you. It's blue shifted, the frequency gets higher if it's going away from you. So you don't scan precisely on 1420, you get to learn according to which bit of the galaxy you're looking at, whether it's mostly coming towards us or away, and you choose your start and stop for your scan accordingly. This is just to try and explain it. So you've got a frequency. This would be the frequency scale along here on your old dial, and there's the S-meter readings. I'm not very happy with that slide, but it'll do. Now, one thing you've got to take into account is the fact that it's all moving, the hydrogen's all moving, but so are we. We're going round once every 24 hours, and so it depends on our latitude, what that velocity is. If you're at the North Pole or the South Pole, your velocity there is 0, but if you're at the equator, you're belting around at, what, 2,000 kilometres an hour or something. We're meanwhile orbiting the Sun at about 30 kilometres per second, which is starting to become highly significant if you're trying to measure velocities relative to objects around you. And the Sun as a whole is moving at about 20 kilometres per second within what we describe as our local part of the galaxy, the local arm of the galaxy. And by local, I mean out to about 5,000 light years. That's the local bit of the galaxy, and we're sort of moving within that. And luckily, we use a system called the local standard of rest for these observations. And luckily, there are a number of online calculators, and it's only necessary to do that calculation once for every series of observations that you're making over a period of a few minutes. So you do that once, and as I'll show you, I've got a spreadsheet I put it into, and it sorts all the data out. It was quite amusing. I lost access to this software, or this program, online program, at one point, and was a bit worried. And the guy who'd written it had moved from one university to another. And while he was moving from one university to another, he had lodged the software, the online server, if you like, somewhere new. I found it, and it came back and said, you may not have permission to use this software. Somehow I got round it. But it was for the Center for Applied Supercomputing in Champaign, Illinois. I was ever so pleased to have got back with it. But there are several calculators about. So, if we're going to use this system to make some observations, this is sort of what we do. We point the dish at the particular part of the galaxy, in this case, that we want. And to do that, we actually start usually with galactic coordinates, because it's easier to think of the galaxy. The galaxy is a disk. We use galactic coordinates, which are longitude going around the disk and latitude coming up and down below the disk. And there are again online converters that you can use. So you say you want to look at, say, galactic longitude 84 degrees and 0 degrees of latitude means you're looking precisely in the plane of the galaxy at 84 degrees, which happens to be where Deneb is, and is quite interesting. So you then convert that into celestial coordinates, right ascension and declination, tell the system to go and find it, and whirs and clunks a bit, and when it gets there, you can then start the scan, and that is done by telling the PIC to do so. And in this case, you can see it started at 1420.00 megahertz, and it proceeded in 10 kilohertz steps. And that's the way the observations are basically made. Having got the observation data in my system, I simply cut and paste the numbers out of the log, which is hyperterm. I'm using hyperterm. Some people use some slightly more modern things, but I'm an old-fashioned sort of a person. And I simply paste it into a spreadsheet. And that spreadsheet I have gone and calculated the correction for the local standard of rest. So it's in there, and this will convert the it does the conversion of the frequency into velocity. That's the basic, let me just think how this, right, okay, that's the basic Doppler shifted velocity, and then a bit further over here it's corrected for the local standard of rest. And so that produces a load of numbers which are all pretty boring, but lo and behold, you can make the spreadsheet produce a plot. And so the bottom scale could have been frequency, but we've converted it into velocity relative to the local standard of rest. And lo and behold, looking in that direction, you see 3 peaks. A dirty great big one at 0, and that's the hydrogen around us, the local hydrogen, out to about 5,000 light years. And in this direction, the other peaks are the peaks associated with other arms of the galaxy. So this data represents 1 pixel. It's slow work making images with amateur radio astronomy. But one of the guys that was helping with this came up with a nice tool using this image, which I'm sure many of you will have seen. It's a NASA image of our galaxy. It's an artist's impression. Obviously, if you wanted to take a photo like that, you would have to fly out of the plane of the galaxy by about 100,000 light years and look back, and nobody's done that yet. But what it does is you can click on any point of the galaxy, and it will show you the rotational velocity that we have recorded and the velocity relative to us. We live near the Sun, that's where the Sun is relative to the centre of the galaxy, and that helps us to identify the peaks. What you're seeing over here, that is the plot at 0 latitude. I can't quite read that, but I think that's probably the plot just looking 4 degrees above. And you see that the two of the peaks are beginning to disappear, and you've only got to look about 8 degrees, I think that's probably about 8 degrees up, and you've lost the other 2 arms of the galaxy, because by parallax they've disappeared. We're still seeing our local bit, but the other ones have disappeared because just by parallax. And by making loads and loads of these measurements, you can start to get an idea of the shape of the galaxy. You can present the data in different ways. This one we're looking in latitude. This is where the latitude is on this scale here. So we're looking up above the plane of the galaxy and down below it, and you see the hydrogen. I think I'm right there. And then here is the peak associated with another arm of the galaxy. I won't dwell too much on that because it's... As you go round, here we're looking round, or I'll go to the next one. Here we're looking around the galaxy at different galactic longitude, and you can see, looking at 0, there's 0, that's the peak associated with our local hydrogen. You can see it's getting a bit confused here, but some is coming towards us and some is going away from us in that particular direction, looking out there. I won't dwell on this because it's rather... We take a little trip around the galaxy with this type of representation. You can see the peaks all shuffle and move. Now, it is possible, and with the little group that I've been working with, we kind of ran out of steam at this point because none of us were good enough at graphics. But it's possible to take this data and create, if you like, slices through the galaxy. This is looking in one particular longitude. Planet Earth is back here, and I've left the local hydrogen out of this particular demonstration, or this particular representation, and I've simply marked onto here lines which roughly represent brightness, the strength of the signal, if you like, and each of these bodies represents represents different arms of the galaxy. The scales here are totally arbitrary, and I'm using artistic license in this. Perhaps it would be better explained if I move to the next slide. This one actually is the local hydrogen around us, and here I've cheated because I had to use data from the southern hemisphere to add to my data from the northern hemisphere, and luckily that data is available, and it shows a slice through the plane of our galaxy just for the local hydrogen. And the thing that amazed me from an astronomy point of view is how flat it is. You can then combine that excuse me, you can combine that with the other images, and you can start to imagine a slice through the galaxy. And if you were to do that for different longitudes in slices, you can imagine that you could build up at least an artist's impression of what the galaxy looks like. It would have been lovely to get to the stage where we could put it into a 3D printer, but we ran out of steam at that stage. But you can see that you can find out quite a lot about how the galaxy moves just using a little dish in the backyard. Now, one of the things that did come out of it was the rotational velocities that we measured, which don't comply with what science predicts. If you have a disk that's rotating, a solid disk, then the velocity of any point on that disk is proportional to the distance from the centre of the disk. We can all understand that. A record rotating, some people remember records. Some of us remember wax cylinders, maybe. Our galaxy, we can see from the observations, most of the mass appears to be at the centre, something that is in common with the solar system. So we would expect that it might obey the same rules as the solar system, where most of the mass is in the sun, planets are orbiting the sun, and Mr. Kepler came along and he worked out how the planets were moving with his laws of and he found that the velocity of the things orbiting the heavy object at the middle was inversely proportional to their distance from it. Mercury whizzes round at about 45 kilometers a second, Venus 35, the Earth at about 30, Mars at about 27, Jupiter is further away and it's down to about 12 or something, and Saturn is loafing around at about 10 kilometers per second. That's what Kepler and Newton tell us to expect. but when we plot the rotational velocities that we observe, we find the line is more or less flat on the part of the galaxy that we're able to observe from Hampshire in England. And that shows us that there's something, some explanation, some other explanation is needed, and that is where we start to wonder about dark matter and dark energy. It's a bit cool to be able to demonstrate that from the backyard using basic radio stuff. So that's really it for the for this section. I think probably a good time if you want to have a break, and then we go on to Goonhilly.
I think we'll take a 5-minute break, guys. Grab coffee or something and then move on to the Goonhilly stuff.
Any questions in the meantime, I guess?
I was wondering about your antenna temperature. So if it's a warm day, is the temperature any different from
No.
if it's a cold day?
No. Well, it probably is immeasurably different, but no, not really.
So
No.
what's the temperature you're measuring then?
It's the energy generated inside the basic noise temperature of the antenna is the temperature of the low noise amplifier, its electrical temperature, and because it's high mobility. And if you look at if you point at a sensitive antenna at the ground, you see the ground temperature. If you point it at a sheet of metal, you see whatever is reflecting off that sheet of metal. You don't see the ground. And this is the way radar works on stealth aircraft. They don't transmit, they look for... so it's down to the performance of the devices in the low noise amplifier and everything after that, but hopefully you swamp that with lots of gain in the low noise amplifier, and the spillover, particularly the spillover of the feed to the dish. If they're seeing anything outside the dish and you're pointing up there, you're going to be seeing the ground behind the dish. So that's what determines it. And we work very hard to minimise that. And in a professional astronomy system, they would use cryogenic cooling and all sorts of things. But to get to that sort of temperature is possible with, standard parts used in TV LNAs. Any other? I'll do a little bit about Goonhilly, which has been occupying a certain amount of my time over the last couple of years now. How did that happen? Well, starting with the history of Goonhilly, it was one of the first ground stations for satellite communications, starting with GHY-1, also known as Arthur, which transmitted and received the first TV signals across the Atlantic with a low Earth orbit, what we would now describe as a low Earth orbit satellite called Telstar. So it really kicked it all off a very long time ago. It was carrying satellite traffic and ended up with many, many dishes until around about, probably out of sync with what it's saying here, but it became redundant as satellites became more sensitive, didn't need big dishes, and then of course the traffic switched from satellite to undersea fibre optic cables. As it turns out, those fibre optic cables still come up to a little room in Goonhilly. Virtually all the transatlantic ones do that come to Britain. But British Telecom abandoned the site, more or less, and I think they actually sold it to a bunch of satellite engineers for £1 or something like that. And these guys have taken it over, and they're called Goonhilly Earth Station. Let's move on to the next one. So, I think those are the three antennas that remain, the three big antennas that remain on the site. There are an awful lot of smaller ones. GHY-1 Arthur is the one that was involved with Telstar, and I think it was also involved with relaying Apollo stuff. In fact, the guy at Parkes, who I was talking to on Monday, is researching all this because it's a very interesting story of how those pictures were got down from the moon. As I'm sure you all know, they came first via Parkes, but the way they were transported around the world is mind-boggling because various things had gone wrong, and the way that pictures were converted, because it was not a scan system that corresponded to anything that anybody had, and it involved a little screen, he was telling me, in a Vidicon pointing at it. And what's worse is that the original tapes of this have been lost by NASA, and they've spent a lot of money trying to find them, and they appear to have been wiped. So,
there was a backup copy apparently.
well,
An official backup copy.
the man you need to talk to, he gave me a long spiel on it, and it's very interesting that they thought they'd found backups, and they think there is, they do think there is a backup that somebody has got that they shouldn't have, and it's too delicate to extract from them. It's an ongoing story, a huge amount of detective work. Watch this space. Anyway, what happened was that a bunch of radio amateurs, and I think quite a few of you guys in Tasmania are involved with amateur television, and a couple of my locals are very much involved with the BATC, the British Amateur TV Club, and they were also involved with the satellite people, amateur satellite people, and were approached to see if they could link Tim Peake, who was the British astronaut who went up on the ISS, if they could provide a link between the ISS and schools so that schools could communicate and interview and so on. And that's how they got the door open, if you like, at Goonhilly. They were asked in to do that. They did it. Noel, GTZ and various other people met with Matt Crosby, the chief scientist, and that was done. It was very successful and ticked all the boxes in their STEM education aspirations for Goonhilly, and everybody was very happy. So the door opened, and then we were invited to come and have a go at playing with this system and see if we could do some EME and other things with it. It was all a bit heavy going because the descriptions I was getting at this stage, they had called me in because I'm an EME person and do radio astronomy, and I was saying, give us a clue, what is the interface to the antenna? You know, is it some sort of rectangular pipe type thing, waveguide? And if so, would you mind telling me what size it is so as I could have some idea? And I got fairly vague answers to all this, and it gets worse. But we got there and we found it was, what was it, Waveguide 11A or something. It was one side, and I forget the other side, but it was fine for 5.7 gigs. We measured the return loss on transmit, and on 3.4 gigs it was 8 dBs return loss, not very good. But we had, luckily, somebody liberated some circulators from somewhere, so we were at least able to protect the PA. We fired all this up, and we were getting massive echoes off the moon. What a surprise, with 50 watts. And this, I think, is probably one of the early attempts where we were trying to make things work. We did some tests. In fact, we were aiming, the TV guys were desperate to try and get TV moon bounce. Now, I think anybody who's been involved with moon bounce knows that that's going to be one heck of a problem because of the phase distortion, because of the shape of the moon. But they're still very keen to try it, and I'm trying not to be too negative about that, shall we say. Here's my transverter that I was using, and it's somehow plumbed in transmit and receive. The waveguide comes down, you've got left hand and right hand circular polarization ports for each, and you're obviously transmitting right and receiving left. If this is going to work, you probably gather we're testing with this guy. We were supposed to be testing, and indeed did tests with Bochum, the ex-Apollo base station in Germany, which has been brought back to life and has amateurs have access to it. Unfortunately, they cobbled together some sort of patch antenna as a feed, and they were not much of a signal off the moon. We need to have words with them and get them to put a decent feed on the system. I'll just run that again. I should explain that the first voice you hear, which is mine, that's my echo off the moon. It's not me locally. So we'll do it again. We'd only worked him once before. The as usual bit is a bit of an exaggeration. I should explain that we weren't quite sure how I should sign, so we signed portable. I think portable with a 400-ton, 32-metre engine. On reflection, possibly we could have come up with a better choice. But there we are. Now, I don't know, I expect you've probably all seen this, but the next thing that happened was Goonhilly heard that Michael Portillo, who does his railway journey programmes, was coming down to Cornwall, and could we arrange to bounce his voice off the moon, which we did. Has everybody heard it?
No.
Some of you haven't. Well,
Go for
in a minute we'll see if we can link up on the internet. There's a YouTube clip we can get to. But that was great fun, and of course this was helping to build the relationship with Goonhilly. I was asked at Parkes, what is my relationship with Goonhilly, and I think I managed to dodge the question in the end. But it's basically unpaid consultant. Dog's body.
Subject matter expert.
Provider of quick and dirty solutions, and that's really all it is. And there we are afterwards. Anybody who's seen Mr. Portillo's programmes knows he always wears some very bright garment. I tell people that I went into the local tailors in my nearest town, Andover, and said, "Have you got a pair of bright green trousers?" And they said, "No, so we don't get a lot of call for that sort of thing around here." Now this is starting to get more interesting. This is part of the tracking system, positioning system, because remember it was for geostationary satellites. And one of the guys on the team at Goonhilly, we explained, that you need to be able to track stuff if you're going to look at satellites and space and things. And this is a part of the control system. It's 1984 vintage. There are banks of thyristors and things that control the various motors. And he dug around inside the works, and he found a cable with a, 64-way or whatever it is, D-type. And that connected the box where you set the azimuth and elevation you wanted to the thyristor stuff that controlled the motors and read the encoders. And he went on to eBay and he found a cable that would fit that plug and come out, fanned out at the other end, just flying leads. And he went on to eBay and he found a board that has Ethernet, let me point to that, Ethernet coming in and a load of I/O. And in that way, the 1984 vintage system was interfaced to a PC. And he wrote the software. The motors that are driving the azimuth, here is one of them. They're fairly substantial, 4 of those. And at one point we were trying to operate EME. We were trying to work a VK station. Actually, I'm ashamed to say I've forgotten the guy's call sign. Somebody will probably tell me. We were trying. We had a sched with him, but we wanted to check Taurus or something, which meant trundling the dish round through 180 degrees. And at that point, trips went on 2 of the motors, and we couldn't get them to go back. So we were moving at sort of half speed. It was all pretty dreadful. But this particular antenna is now in the process of having £8 million spent on it to take it into the deep space network. So all these things are being sorted, which is good. The bad news is I probably won't be able to use it anymore, play with it. But if possible, I will. This is amusing in that it's part of the transmit system. It all looks immaculate in there. It looks as if you could fire it up tomorrow and you'd be cooking with gas. This is on transmit, it transmits left-hand circular and right-hand circular up on 6 gigs, and the satellite was down on 4 gigs. This is one of those, I don't know if it's the left or the right-hand circular polarization transmitter, and it's standby, and they ran, I think it was 3 kilowatts each, and they have travelling wave tubes in them. It's the prime mover, and there is one of the travelling wave tubes, and there is a letter releasing 2 of the travelling wave tubes from stores. Cost £80,000. We found that lying around there, and I had to photograph that. It's taken quite a few visits there to really understand how the system works. It's a beam waveguide system. It's a shame should have had these slides around the other way really, but the way that works, it's a Cassegrain system and a great pipe with rotating joints with mirrors in it that brings the signal down to ground level. You'll see more of it in a minute. And they're a bit sniffy about letting me get into it and find out how it works, because I desperately wanted to bypass some of the stuff in there which was frequency sensitive and giving rise to this 8 dB return loss. But they were not keen on letting me scrabble around inside. But eventually one of the guys, maintenance guys, found a manual, and I photographed the diagram that shows how it works. Basically, it's a very long horn, and there are, I think they call this ortho mode junction. So you've got 2 ports for each band into this strange looking horn, and the polarization is accomplished using phase shifters. I think the next diagram shows you how it sort of works. So here's one band. There are 4 ports for each band. Here's one band. You've got left hand and right hand coming in. There are phase shifters and filters and things to launch or to receive the signals left hand and right hand. And a bit further down the horn is the same again for the higher band. Again, phase shifters and so on. And a bit further down still there's actually a KU band feed on this. But because of the way it works, the illumination angle of a horn with a fixed aperture obviously is inversely proportional to the frequency, or is inversely proportional to the wavelength. So when you get to KU band, it only illuminates a small part of the dish, but at 4 gigs and 6 gigs, it's more or less illuminating a lot. And this horn actually, I'm going to skip that and come back to it. So the horn comes up from below, very, very low flare angle in sections, keeps on going up and up and up, and eventually it arrives at the aperture, which is here. That's got a membrane across it, and it's pressurized to keep the muck out of it. And as you can see, it's in a pretty sad state here, and it illuminates the first mirror, which is here. So that mirror takes the RF off horizontally, and then there's another mirror that takes it vertically, and that is at the centre of the rotating axis for azimuth. And there's a similar arrangement further up for that's elevator. I bound to have got that round the wrong way, but you'll see some more pictures of it in a minute, I think, outside. But that's the way it works. It's a beam waveguide system, and the aperture of the beam of the waveguide is, you could actually drive a small car down it. It's pretty big. I don't know what they're doing to convert it for deep space, but if it was down to me, I'd use the same system, take away a load of the sections to get down to the right aperture to illuminate the mirror, move it up to the right focal point, and then add the feed systems at the bottom. But I don't know whether they're doing that. Be interesting to find out. I think they've subbed that out to somebody else. So here's the shack there. As a result of the various things that we did, they finally let us have play with it for a weekend, and we had lots of QSOs, and that was good fun. We did various things. So you can see we're set up for 3.4 gigs at one end and 5.7 at the other. We didn't do simultaneous transmissions, and we did interlock the systems, but we think we probably could have got away with it at least one way round without blowing anything up.
What sort of power are you running on
we
each
were running
system?
about 50 watts on 3.4 and 40 watts on 5.7, so not particularly high power, and we just didn't need particularly high power. That's interesting, it's not coming out of the speakers. There's that. Sort of connection or something we've knocked off.
It's all the volume.
Oh, is it?
I think it's a volume issue, sorry.
Yeah. It was coming out. Anyway, it's not too important. It was great big echoes coming out of the. There we are, working away. I think I forget how many we worked. It probably total more than 50 stations in the session. See what comes up next. These are something you've seen that one before. One of the things when you're using a big dish, you have the problem that you're very much under illuminating the moon, whereas the guy with the little dish is over illuminating it. So you don't always seem to get the results you might expect as a result of that. And if there are two of you with big dishes, you've got to be pointing at the same spot of the moon, which adds another dimension to it. And I'm not sure our pointing accuracy or theirs is necessarily up to that. It's something you have to watch out for. Next is just a little trip around some of the other dishes. Goonhilly, you may be aware of, they managed to get €1 million out of the local government to restore it, and now that's very much back in action, with amateurs having restored the radio RF part of it, and the dish itself being professionally restored. That's working away very nicely. And there's the shack at Goonhilly, which is actually part of the dish and moves round with the dish, so it goes merry-go-round. But quite a nice comfortable shack there. That's the 32-metre antenna in Italy, which we visited with one of the EME conferences a year or two ago. It was quite funny because a busload of EMEers was decanted onto the site. There was hardly anybody about. We were all scrabbling around inside it, and then some of the staff came out and were absolutely horrified at where we managed to penetrate. So that's about it. This slide's not particularly up to date, but one of the options at Goonhilly is that GHY1, if somebody's got a spare few million, it could be restored and brought into operation to play with. And to begin with, we were thinking we would try and put some sort of consortium together to do it. But talking to some of the riggers down there, they were saying it's a bit of a basket case surface-wise, and it's going to be a huge labour of love. Somebody may well do it, but what happened was that its almost sister dish, GHY3, has become available, and we are likely to have access to it. A new feed arrangement has been designed that can carry different feeds, and indeed I've made a feed for it to work on 3 gigs, not the amateur band unfortunately, but I can easily make one for the amateur band, and we can hopefully go down there and have a play with it in the future. Other things that we've been asked to do in our sort of consultancy basis, one thing which was quite amusing. There's a local 20-metre dish near me at a place called Bolton, and it's normally used as a weather radar with its unambiguous range is about 200 kilometres, not limited by its power, that's by the pulse repetition frequency, and it's used for weather. But they wanted to see how it would be at looking for space junk. And so we went down and used GHY6, made up a quick receiver by converting a 9-SEM converter. Working on its image, we could work on their radar frequency. And we did some tests looking at echoes of the ISS, which is an enormous object, and if we couldn't get echoes of it, it would have been something seriously wrong, but we were getting massive echoes of it. And next time we go down there, we will be doing things slightly more professionally. I reckon we'll be able to see CubeSats. So it's a bit more fun to be had with Goonhilly. Okay, I think that's about it. Any questions? Should we try and get that clip from Mr. Portillo? It's all good fun, and hopefully we did get in their good books enough that we were invited to their Christmas party. So there we are. Any questions?
Is there a moon pies?
Real big boys' toys, aren't they?
They are. It was wonderful to play with them, it really was. I think there will be further opportunities, but it'll be with GHY3 when it gets its new feed carriage installed. Unfortunately, it's a job that requires a crane, and we were there in January, and Goonhilly is on the Lizard Peninsula. It's kind of windy there, and they don't want to do anything with a crane until there's a chance that the weather's reasonably stable for 6 days, which is not going to happen in January or February. Maybe they'll be getting on with it now, I hope so.
Yes, Marconi had enough trouble with Polju, didn't he?
He did, yeah. It's very windy.
Brian, you mentioned the 50th anniversary of the Apollo missions and possible Goonhilly involvement earlier.
Yeah. I'm not sure at this stage exactly what they're going to be doing, to be honest. It's very much current, and I'm going to be talking to the guys at Goonhilly when I get back, and relaying what I've learned from the guy at Parkes and what they're doing, and we'll see what's happening. I know what I'm going to suggest that they do. I've suggested that the guy at Parkes, if he can set up, if he can sit and listen on 1296 and perhaps set up a web SDR, then we'll see if we can find some guys in the States who are the big guns in the States to have some QSOs at a appointed time, which Parkes will want to be the week before, because the moon is not in a happy place during the actual anniversary. And I'd rather like to do something similar at Goonhilly. We can't talk to each other because Parkes can only go down to 30 degrees elevation, and at 30 degrees elevation it can't see Northern Europe off the moon. We're lucky at Goonhilly, we can go down to 0, although they're not very happy about us transmitting at 0 elevation.
Can't understand why.
No. Seems very unreasonable to me.
Very good.
So, excuse me, what gain does that dish have?
I'm glad you asked that. I have got the numbers somewhere, but not particularly in my head. It's something north of 50 dBs at 5.7.
What sort of beam width?
Very small.
Like sort of.
I think it's at 5.7. I seem to remember the number is the 3 dB number is it's less than 0.2 of a degree anyway.
Yeah, right, okay.
But actually, I did all those numbers using the rate great VK3UM
Calculator.
EME calculator.
Yep.
Put the numbers in there. It's 32 metres, and Doug sadly missed.
Definitely. Fantastic.
Okay, well, I guess if there aren't any more questions, I'll put hands here and thank Brian for coming all the way down here to talk to us. And it's a very, very cold and interesting evening. Thank you.